Let's consider this problem. Suppose that we have an oil company that's operating 2 refineries. Refinery 1 has an output of 200 barrels of low-grade oil per day, 100 of medium grade, and 100 of high grade per day. Refinery 2, we're also given the outputs per day. We want to produce at least 1,000 barrels of low-grade oil, 1,400 of medium, and 3,000 of high-grade oil to fill an order. We're given the operating costs per day for each refinery, and we want to determine how many days each refinery should be operated to meet the requirements at minimum cost. So the first thing we want to do is define some variables. Let's let x1 be the number of days that refinery 1 is open, and we'll let x2 be the number of days refinery 2 is open. And we want to determine what we are optimizing. We know we want to minimize cost, so that tells us how to set up our objective function. We want to minimize cost. I'll call it C. And what will C be equal to? Well, it costs $20,000 a day for refinery 1. So if I multiply that 20,000 times the number of days, and I will write this as 20x1, and then the second term will be 30x2 because refinery 2 costs $30,000 per day. We just have to remember that our costs are, instead of being in dollars, they're in thousands of dollars, and it's just fine to set it up that way. You just have to remember what you did so that you know what your actual cost is at the end. Okay, now let's write down our constraints. Okay, we have a constraint for low-grade oil. We know that we need at least 1,000 barrels of low-grade oil. Okay, how do we get that? Well, how much does refinery 1 make? 200 per day. So I take that 200 per day multiplied by the number of days the refinery is open, which is x1. Then I do the same for refinery 2. Refinery 2 makes 100 per day times the number of days it is open. And so that's our first constraint. Now for the second constraint, we know that we need at least, thus the greater than or equal sign, 1,400. This is for the medium. So for that we have 100 x1, and then we move to refinery 2, which makes 200 barrels of medium per day, so we get 200 x2. Now we move to the high. We know we need at least 3,000 barrels per day here, so we look for the barrels of high grade oil, the output for each refinery. 100 for the first refinery, and then second refinery makes a lot more, 600. So 600 x2. And we ask ourselves, would it make sense for either of our variables to be negative? No, it wouldn't make sense to be open for -3 days. So we're going to write down our non-negative constraints. It's important that we make sure we have those. If we do not, then we do not have a standard minimization problem. Here we have a standard minimization problem. We have a linear objective function and constraints. Our objective function is being minimized, and we have greater than or equal to a positive constant on each of our constraints. And so that means that we can use the dual. If you have mixed constraints, some less than or equal to, some greater than or equal to, or if you have a maximization problem, you cannot use the dual. You have to use a more advanced technique. So it's important that we note that we have this. So from here we want to write our matrix that gives all the coefficients for our constraints and our objective function. Let's do the x1. Well, x1 will be in the first column, x2 in the second, right hand side in the third. Let's start with our first constraint. We'll have 200, 100, and 1000. And if you want, you can write a vertical line to separate out your right hand side. Second constraint, 100, 200, 1400. Third constraint, 100, 600, 3000. And now our objective function, 20, 30, and then whatever you want over here. Now we write the transpose. So our A transpose then, each of those rows will turn into a column. So we will have that 200, 100, 1000 that is going across the first row will now become a column. So we have 200, 100, 1000. Our second row would become a column, 100, 200, 1400. Third row becomes third column, 100, 600, 3000. And then our last row, 20, 30, and whatever. Okay, we use these to write our dual problem. Okay, we are going to be maximizing. Okay, in the first problem we were minimizing C. Here we want to pick a different letter. Let's call it P. We're going to maximize it. We're going to get the coefficients from the bottom row of our transposed matrix. So we're going to have 1000. Now what do we do for variable? Choose different letters. For the original problem we had x1 and x2. So now we're going to use y's. So 1000 y1 plus 1400 y2 plus 3000 y3. Okay, then subject to our constraints. These come from the top two rows. So 200 y1 plus 100 y2 plus 100 y3 less than or equal to 20. Remember, this will be a maximization problem. The directions of our inequalities will now be less than or equal to. Second row gives me 100 y1 plus 200 y2 plus 600 y3 less than or equal to 30. And then I have all of these decision variables non-negative. This is our dual problem. It's very important that you know how to write this down. Once we do this, then we go back to simplex to solve it. So that means we're going to have to write our initial system with our slack variables. Okay, so for our slack variables, we are going to use the original variables as those slack variables. So we'll have, when we write our constraints, 200 y1 plus 100 y2 plus 100 y3 plus our first slack variable, which will be x1, is equal to 20. Move to our second constraint, 100 y1 plus 200 y2 plus 600 y3 plus another slack variable, that will be x2, equals 30. Now we do our objective function, but we subtract everything, all those coefficients, over to the left side with the p. So now we have negative 1,000 y1, negative 1,400 y2, negative 3,000 y3 plus p is equal to 0. And of course, in that initial system, my x1, x2, along with my y1, y2, y3, all of these are non-negative. We use this system to write our initial simplex tableau. This has so many columns, you will probably want to label them to make sure you don't get mixed up. And give yourself enough room to put relatively big numbers in there. Okay, so for y1 I have 200, 100, negative 1,000. y2 I have 100, 200, negative 1,400. y3, 100, 600, negative 3,000. x1, 1, 0, 0, 0, 1, 0 for x2. 0, 0, 1 for p, then 20, 30, and 0 for my right hand side. When you wrote all this up, it certainly would have been fine if you wanted to measure your oil in hundreds of barrels instead of in barrels the way I did. In that case, in your first column you would have 2, 1, and negative 10. Sometimes that makes things a little more manageable. But I've done it this way, so I'll continue this way. Okay, now we need to determine our pivot element. First, starting with the column, we choose the most negative, which would be right here. Then we move to the right side and calculate the quotients. So we have 20 over 100, which would be 1/5. We have 30 over 600, which would be 1/20. So that is certainly smaller. So here is our pivot element. So we do the pivot. I'm not going to go through the row operations here. I'm going to assume you either can do them by hand or are using some kind of technology to carry out your pivot. When you get it done, here's what you should get. Under x2 we have negative 1/6, 1 over 600, and 5, 6, 0, 0, 1 under p. And under my right hand side I have 5, 1/20, and 1/50. So now I look again to determine my most negative indicator in the bottom row, and that would be this negative 500. So that gives me my pivot column. I calculate quotients over on the side. So I do 5 divided by 550 over 3. Which would be 15 over 550. Which is about 0.027. And then for this one, I have 1/20th over 1/6, which would be 1/20th times 6, which is 0.3. And so we want to go with the smallest, which will of course be that top row. This one's the smallest. And so that 550 over 3 is my pivot element. Sorry about that. That should say 550 over 3. And so we pivot around that. And then here is what we should get. Under Y1, 100, Y2, 4 11ths, 3 11ths, and negative 2400 11ths. I have mine written as fractions. Yours may be decimals, and that's fine. 0 1 0 under my Y3, 3 over 550, 0, 30 over 11. These are the numbers that make you want to do this with a computer and not by hand. 0, 1 over 550, then 50 over 11 for my P, 0, 0, 1, and for my right hand side, 9 over 110, 2 over 55, 2100 over 11. So now I look for the most negative, and actually I only have one negative, and that is right here. So that certainly gives me my pivot column. And now we want to calculate quotients over on the right side. So I take that 9 over 110, divide by 4 over 11th, and I should end up with 9 over 40. Which is 0.225. And then in my second row, I take that 2 over 55, divide by the 3 over 11, which should give me 2 over 15, which is about 0.13. So that is certainly the smallest, and so that gives me my pivot row. So there's my pivot element. So I do another pivot. When I do it, this is what I should get. Under Y1, I have 1 0 0 still. Under Y2, pivoted there, so I have an identity matrix column in that row. Y3, I should get negative 4 thirds, 11 thirds, and 80. X1, 1 over 150, negative 1 over 300, and 2. And in the X2 column, negative 1 over 300, 1 over 150, and 6. P, I have 0, 0, 1, right hand side, 1/30th, 2/15ths, and 2/20. Okay, so we have no more negatives. We have no more negatives, so that means we are at the optimum. Remember, for our negatives, we're looking in the bottom row. So that tells me we are at the max. Let's write down the solution to our dual problem and the solution to our original problem. Okay, so remember your dual problem had variables y1, y2, and y3. And so y1 is equal to 1 over 30, and y2 is equal to 2 over 15, and y3 is equal to 0. Non-basic variable with junk in the column. Okay, and our P that we were maximizing is equal to 220. Okay, now let's write the solution to our original. We really don't care what the solution to the dual is. I'm just writing that down so that you can be aware of the distinction between the original problem and the dual. So, our original problem had x1 and x2 for the variables. Okay, so we need to figure out what those values are. These come from the bottom row in the dual. So here's x1 and x2 in the dual. Here is the bottom row. So x1 is equal to 2 and x2 is equal to 6. Our original C, which is what we were trying to minimize, is the same as the maximum of P in the dual, so that will be 220. So this is the solution to our original linear programming problem. Now we need to interpret that solution in terms of the original problem, the paragraph that described the scenario. So let's do that. So we were asked how many days each refinery should be operated to meet the requirements at minimum cost to the company. So here, remember, x1 represented the number of days that refinery 1 would be open. x2 was the number of days refinery 2 was open. So refinery 1 for 2 days and refinery 2 for 6 days for a minimum cost. And here's where you want to look back and see what units your cost was in. Remember, we had ours written in thousands of dollars rather than just dollars, so this really means that we would have a cost of $220,000. I hope this helped you to understand the dual method. Good luck, and I will see you next time.